Well, I'm from Rockhampton, so I thought I came longest way to this workshop, but I just found Sean beat me by 500 miles more. Right. That's the talk. Well, my talk here is just to share my experience with colleagues here. Last year, I was invited to a Glaston community year 10, year 11 student, well, every year's math and science challenge. Move? Which one's move? Okay, thank you very much. Yep. I went to there, Saturday morning I went to there and I found about 40 year 10, 11 students there, along with the teachers and the professionals and engineers there. I was invited simply because a month ago I gave a similar talk to Engineers Australia Central Queensland Division about this topic. So I was a trained geophysicist and of course a mathematician. So they asked me, I did. So one of the audience members there, he was in Glaston. He asked me, I'll come to here, present this to the students. It will be fascinating. So I went to there, talk about this. I came from China 20 years ago. So look, China and other countries as very, very seismic active. So I presented from here, just gave some sort of virtual impact for the audience, say how earthquake can impact to the society, people, lives or whatsoever. And here, just to start from here, our own, right? And move on to here, so I graduated from UWA, so I know this one. I went to this site. It's so far the largest earthquake in Australia inland. And now today I went through this one, and then wherever the interaction between the audience students, I will stop to show what's the problem or what's the reaction from students and teachers and engineers. So another one, 2 days ago, Taiwan, another earthquake happened. And this is our neighbor, as New Zealand, and this is a Christchurch earthquake. And funny enough, the second one, the aftershock, actually caused more damage to the main shock. So just showing quickly here. And this part is very, very good. I put something there, it's a circle here. I added there. I showed the way, just want to have some fundamental knowledge to the students. Talking about here, sorry. So here we're talking about Australia. This is plate tectonics. I ask audience, do you know anything about plate tectonics? Tectonic. The students say, okay, we know about it. They're good. Probably they learn this from science subjects. It's really good. Then I ask students here, so New Zealand, here us. So what the difference between New Zealand and Australia in terms of earthquake activities? Almost no one could answer my question. So I put it in there. I told them the way is just geologic settings. We are here. So Australia is very lucky. The entire plate. So we are in. And here in New Zealand, our neighbors is unlucky because they are sitting on the subduction zone. It's every day, everywhere, including around this area, an earthquake may strike. So that's an unfortunate situation. But we, Australia, we are very lucky. And then we move on to here. This is our own region. Further explain to students here. We have some small dots here. This earthquake is in Australia land is actually we refer to as an intraplate earthquake. It's normally small. But here is interplate earthquakes. Two plates clash together, or in strike slip or subductory underneath. That's the difference between Australia and New Zealand. So this, I think it's from this point on, student they were very, very interested, because this is more close to life. And quickly move on to explain fundamentals about earthquakes. I asked students, well, you got knowledge about physics. This is not beyond your knowledge of understanding about physics. And this part is well received. Students, oh yes, we know this part. Right, that's good, and then we move on. What we need is an earthquake. From there, actually, it's not about earthquake itself. It's not about the focus. It's about enormous power released. That power actually translated through the media from the earth, the crust, and by the two types of waves, P waves and S waves. That's quickly, I just run through, just gave student there to say, okay, so one way move this, one way move that. This S wave is always very, very destructive compared with P waves. However, P waves travels faster. It arrives earlier. S waves travels slower. It arrives a little bit later. So that gives us a clue and how we are going to deal with the three parameters of an earthquake: it's location, magnitude, and time. So from this one, we're more interested from here, the difference, the interval between P waves and S waves. So first arrived P waves, second arrived S waves. We need this part, and to determine the three parameters of an earthquake. They get the student on, they want to do more, they want to know more, and say, here we have a scenario, I'll put it here, because the P wave travels faster on average this, S waves is slower on average that. We need that one to determine where the earthquake just happened. Then move down, here is the way. We assume that one, we just assume that three earthquake or seismic stations in Gladstone or central Queensland. Gladstone, Rockhampton, and Bundaberg. And the different time intervals recorded. Then we use that one, use this formula. We calculate it's about 900 kilometers from Gladstone, and about 1,000 kilometers from Rockhampton, and about this distance from Bundaberg. And a good point, the next one. Then how we are going to locate where the earthquake occurred is here. Then I asked student how we are going to locate this one. One girl put her hand out. Yes, we know. We just need to draw three circles. We need the intersection point. That's it. That's really good. So that means our science subject covered part of that, and that at least one still remembered, but the rest did not. So this is exactly we showed from this picture. We just draw three circles, and then this is the way. Three circles intersect together. And further, I asked students, well, can we determine the location if we just use two circles? I feel, oh no, simply because if two circles, we are going to have two intersection points. So three will have a unique solution. So this just reflects in our curriculum, senior high school curriculum, some knowledge already covered. But this way, only few students that they can remember or they understood those. Right. The move on, that's why how we are going to determine where the earthquake occurred. Then the other one, the magnitude. Students know Richard scale. And this one, we just simply using eye sample to simulate. And here we're talking about this formula. Put the dose in, amplitude in, and then calculate. Here the one, I'll just put it here, circle here. When we had this calculation, I asked students, look, I use this, 998. I just use 1,000, put it into here to calculate. Can anyone explain why I use that one rather than 1,000? Sorry. 1,000 rather than the exact value. Only one engineer put hand up. Yes, I know. Because if you put the 1,000 in from here, you will get 3. But log 1,000 to base 10, you get 3, exact number. Exactly, this is somehow to remind the students, it's the idea of approximation. And because the way is, Richard scale is cut off one decimal point. So most likely, if you put it here, the difference will be 2 or 3 decimal points. So that doesn't change this. So this somehow is, I refer the topic as mathematics everywhere. So if you pay attention to, then you can relate mathematics into everything almost. Right. And this general knowledge about there, and then move on to topic is about principles of tsunami warning system. How does it work? Right. This is Japan earthquake. That was the talking point back to a few years ago. Then move on. We have some physical assumptions. And we just assume that one earthquake just occurred there. Okay. Then this about this. Here, tsunami is about the big waves traveling from ocean. So that is not about P waves, not about S waves. It's about the speed of the water waves from ocean. So this on average is like that. So given those, now we can calculate in such a way, this big wave would arrive Vandenberg about 1 hour. Well, Gladstone about 71 minutes in such. And then we know if we are going to take 10 minutes to get location, 10 minutes to report to authority, we need something, and then take 2 minutes. Right, for that one, we need to take about 22 minutes for the decision to be announced. So given that, it's simple, much simple. Gladstone, you have 37 minutes and or 49 minutes to issue the tsunami warning, right? So that's all about this, and that's much easier. Everyone can understand. Doesn't matter the time is enough or not. But the question here, very interesting here. I asked two students. I asked students who can derive this formula we used before to determine the distance. And the two girls came down to the front and tried to work out from a whiteboard, but they couldn't. And I gave them prize as my book, textbook, mathematics. And then I showed this straight away on the board to the students. Now, look here. It's just the need to do what? Sorry. Here. The simple calculation physics. Here you go. Put those in, and after that one, you get this. And by the time we finish this, everyone, oh yes, that's easy. But no one could do it beforehand. So my point is here, even here. Many students just couldn't work out from this step to that. And later on, right. So this is something I already finished. So I just put a quick comment about last point. The last point, when I finished that one, and the teachers and the engineers, we sit together, and the teacher told me, look, it's really good. The way is our experience was, at least in many Central Queensland schools, the math teachers did not teach students how to derive something. Give them a formula and give some figures, they use calculators just get the value or figure. That's it. That's the current situation in high school math education. So we talk about, well, we probably need to change something. We need, something we need to work with school teachers and to transfer or to change their perception or way of delivery. And in such a way, and first, we don't need students to think about, oh, mathematics is always hard one. Let's get rid of that. Just quickly jump out from that. The last point I share with you, I agree with you and also with Sean. And I also teach first year, second year engineering math. And the first year one, and sometimes can be 50% of students just filed foundation mathematics. It's stunning. So look, we probably need to work together to change the current practice. Thank you very much.
Does anyone have any questions for William?
Probably now it's time for break.
Yeah, I think everyone's getting hungry. Just a quick question for me then, William. So this was a presentation to Year 10 and 11 students and teachers. So what were they, like the top students in Year 10 and 11, or was it just a mixture?
I would suggest they are good students because this is a voluntary activity because every year they have a math and science challenge. Students just voluntarily participate. So I would support they are good students. Yeah.
All right, so if anyone has any more questions for William, please catch up with him at the afternoon tea. Thanks to William and all the other speakers for the questions.
Thank you.